Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. I want to talk about deep residual network, published in the paper entitled as Deep Residual Learning for Image Classification by Kai-Ming He in CVPR 2016. The use of residual network addresses the degradation problem when the network goes deeper. This makes deep residual network widely being used in many applications due to its effectiveness in feature iteration. The outline of this lecture includes introduction about the depth evolution in the literature of neural network and the issue to be addressed when the neural network uses more layers. Deep residual network, about the main idea of the proposed deep residual network, the layout of residual block, and the architecture of the proposed deep residual network. Deeper residual network, about the bottleneck block for building deeper residual network and its architecture. Recent evidence reveals that the level of features can be enriched by the number of stack layers, called the depth of network. Therefore, network depth is of crucial importance in many visual applications, such as image classification or object detection. These two figures show that as the depth of the networks in the literature increase, the accuracy for image classification and the mean average precision MAP for object detection significantly grow. Does the classification accuracy continue growing when we add more layers? Unfortunately, the networks with more layers suffer from the degradation problem. That is, the accuracy gets saturated and then degrades in training and testing. As shown in these two figures, the training and testing errors of the network with 56 layers is larger than the one with 20 layers. Since the training error of 56-layer network is larger, this reveals that the degradation problem is not caused by overfitting. To further identify the reason of degradation problem, the following scenario is used for analysis in this paper. Firstly, we train a shallow network, and its testing accuracy is X. Then we copy the trained layers and add several identity layers to form a deeper counterpart, which have the same testing accuracy. Finally, we train this counterpart and test it as usual. As we know, the model dimension of this counterpart is high. It should have the better performance than the shallow one. But in this case, the testing accuracy of this counterpart is less than X. This reveals that when network goes deeper, finding the solution is not so easy, even when the mapping is identity. Accordingly, the main contribution of this paper is to address the degradation problem by the proposed residual mapping. Based on the assumption that the input S and the target function h of x is of the same sizes, the main idea of residual mapping for addressing the degradation problem is to approximate a residual function r of x instead of h of x. Here, r of x is defined as h of x minus x After residual mapping, the target function h of x is resumed by adding x back to R of x. In transition, the deep neural network is a cascade of building blocks for direct mapping that approximates h of x directly. As discussed, deep neural networks using direct mapping suffer from degradation problem. To address this, the building block in this paper performs residual mapping that firstly approximates R of x by neural layers, and then passes input x for adding back. Here is an example of residual mapping. For an input x, we firstly produce the residual map R of s via a stack of neural layers, and then perform element by element addition of R of s and x to finally obtain h of s. For example, 2 plus 1 equal to 3, and 3 plus 2 equal to 5. There are two reasons for using residual mapping. Since R of s is a referenced function with respect to input s, it is easier to be approximated than the unreferenced h of s. The residual network can be trained by SGD end-to-end with backpropagation. Next, we detail the components inside a residual block. A residual block is composed of several neural layers and a shortcut. In this paper, the neural layers are two convolutional layers. The shortcut to pass the input for addition is either identity or projection shortcuts that will be detailed later. For a convolution layer, it consists of convolution operation, batch normalization, which was proposed in this paper, and ReLU activation. This figure shows the detail inside a residual block. The element by element addition is after batch normalization, but before ReLU activation. For convolution operation, it uses kernels with the size almost equal to 3 by 3, and the number of kernels used for convolution is based on the idea to preserve computation complexity. In more detail, for input feature map X with the size W by H by D, if its trie is 1, the operation uses D kernels for convolution. For a kernel, it produces a W by H by 1 feature map, and thus outputs a W by H by D feature map whose size is the same as input X. If the trie is 2, the operation uses 2D kernels for convolution. For a kernel in this case, it produces a W over 2 by H over 2 by 1 feature map, and outputs a W over 2 by H over 2 by 2D feature map that halves the width and height but doubles the channel number. As for shortcut connection in residual block, it is to bypass the convolution operation and transfer the input to the feature map with the same size as output. There are two shortcuts used in this work. One is identity shortcut that forwards input directly when input and output feature maps are of the same size. The other one is a projection shortcut that maps input size to output size when their sizes are different. These two figures show the identity and the projection shortcuts respectively. When the residual block produces the feature map with the same size W times H times D as input, it uses the identity shortcut to directly forward the input feature map. When the output of the residual block is W/2 times H/2 times 2D feature map, the projection shortcut, denoted as red arrow, transfers the input feature map to the one with the size W/2 times H/2 times 2D. Projection shortcut performs size mapping by convolution operation. To have the width and height, the stride of convolution operation is set as 2, and the 2D 1x1 kernels are used to double the depth. In other words, during convolution operation, using one kernel will produce W/2 times H/2 times 1 feature map. Thus, the projection shortcut outputs a feature map as desired size. Based on the mentioned residual block, we next detail the architecture of the proposed deep residual network. In this work, all proposed residual networks consist of 5 stages, and each of which downsamples the feature map by a factor of 2. In other words, the proposed residual networks downsample the input feature map by a factor of 32. For each stage, taking stage 3 for example, it is composed of several residual blocks, as mentioned before. There are 2 deep residual networks proposed in this paper. One is an 18-layer network, and the other one is a 34-layer network. The first stage of both networks is a convolution layer with a stride of 2. The kernel size and the kernel number for convolution operation are 7x7 and 64 respectively. Here shows the detail inside the first stage. For a color image with size W times H times 3, the output of the first stage is a feature map with the size W/2 times H/2 times 64. Here details the architecture of 18-layer residual network. The stage 2 consists of a 3x3 max plural layer with a stride of 2, and 2 residual blocks with identity shortcut. The stage 3 consists of 2 residual blocks, and its first convolution layer uses a stride of 2 for having the feature size, and uses 128 kernels to double the output channel as mentioned before. For the purpose of size mapping, the projection shortcut is used in this residual block. For stage 4 and stage 5, they have the same layout as the stage 3, but use 256 and 512 kernels for convolution, respectively. Finally, we count the number of layers in this network. Stage 1 has 1 layer. Stage 2 has 5 layers, 1 plus 2 times 2. The remaining 3 stages have 4 layers. There are totally 18 layers in this deep residual network. For 34-layer residual network, it has the same architecture as 18-layer network, but increases residual blocks to the last 4 stages. The numbers of residual blocks at the lower part of the last 4 stages become 3, 3, 5, and 2 respectively. There are totally 34 layers in this residual network. As the figure on the left-hand side, it shows that the 34-layer network has the less training and testing errors than the 18-layer network. This reveals that using the residual block for building the deep network successfully addresses the degradation problem. Besides, compared to existing methods, the proposed 34-layer residual network are with the most layers and has the highest accuracy in ImageNet classification. To make the residual network deeper, this work further proposes the bottleneck residual block, which consists of 3 convolution layers. The middle layer of the bottleneck residual block is a 3 by 3 convolution layer to perform residual mapping as its plain residual block. The first and the last layers are 1 by 1 convolution layers for reducing and increasing the channels respectively. The idea of designing the bottleneck residual block is to make it have the similar model size as its plain counterpart because of concerns on the training time. By taking an input with 64 channels as an example for plain residual block, the model size of each convolution layer is 3 times 3 times 64, number of kernel parameters, times 64, number of kernels. Let the input size to the bottleneck residual block be W times H times N. As mentioned, the middle layer performs the same residual mapping and has the same model size as its plain counterpart. Since the first layer has to output the feature map with 64 channels, it uses 64 1 by 1 kernels and has model size 1 times 1 times N times 64. For the last layer, it uses N 1 by 1 kernels to output the feature map with N channels, the same as the input, and its model size is 1 times 1 times 64 times N. According to the design idea, the model size of both residual blocks should be similar. By eliminating this term and multiply factor 64 at both sides, we have this equation. N is last set as 64 times 4 in this work. In other words, the design of bottleneck residual block is to quadruple the channel number of the input with respect to its plain counterpart. The name bottleneck is derived from the shape of the channel numbers of the feature maps through this residual block. Based on bottleneck residual block, this paper proposes 3 networks with 50 layers, 101 layers, and 152 layers respectively. The 50-layer network stems from replacing all the plain residual blocks in the 34-layer network by bottleneck ones. By increasing bottleneck residual blocks to the stage 4 of the 50-layer network, we have 101-layer network. Similarly, by increasing bottleneck residual blocks to the stage 3 and stage 4 of the 101-layer network, we have 152-layer network. Here is the mentioned 34-layer network based on plain residual block. Then, replacing all plain residual blocks by bottleneck ones results in the architecture of the 50-layer residual network. The total number of layers in this network is computed as this equation. 1817 bottleneck residual blocks to the stage 4 of the 50-layer network results in a 101-layer network. Furthermore, 18.4 and 13 bottleneck residual blocks to the stage 3 and 4 respectively results in a 152-layer network. As shown in this figure, the networks using bottleneck residual blocks are deeper and further improve the accuracy in ImageNet classification. The residual network with the most layers achieves the highest accuracy, about 94.3%. In this video, we firstly introduce the residual block that performs residual mapping instead of direct mapping. The deep network built by residual blocks successfully addresses the degradation problem. To further make the network deeper without increasing model size, the bottleneck residual blocks are used to replace the plain ones in the residual network. The resulting residual network with 50, 101, or 152 layers outperforms the state-of-the-art networks and have been widely used in many applications. Thanks for your listening and have a nice day.